Hi, everyone. Let's try to start on time. We are already 1 minute in. So the introduction is not going to be long because it's one of our own faculties, right? So Alicia did her undergrad at Princeton, then moved to Stanford for PhD doing cold atom experiments. Then she forgot about the light. Usually you see she saw the light. No. So far she has managed. So she went back to Princeton working on superconducting qubit. So very different range of spectrum. Oh, what happened? I guess that's normal. Okay. So she had a very unique career path, and I think we decided that she should join us. And since she has been here, she's been doing fantastic work in superconducting qubit. For those who know superconducting qubit, it's obvious, but for those who don't know, there's an intense industrial work on that front. So I think working, especially in the physics department, and being innovative and being, I won't say competitive, because I think industry is focusing on some other scaling part of superconducting qubit, but being innovative in a research environment is quite challenging and needs bright people like her. So we're going to listen and learn about what she has been doing in the past few years here. Thank you.
All right, so the microphone is good? Yes, I can hear myself. Okay, so thank you, Mohammed, for the very nice introduction. And I'm excited to be here today to tell you about the work going on in my lab, well, a subset of the work going on in my lab. And so since most of you don't work in the field of superconducting circuits, I'm going to start by introducing why we work in these sort of man-made quantum systems and what our building blocks are. And then I hope to tell you about two projects that are going in my lab. One where we use resonator arrays to make sort of periodic lattice systems. And then a second one where we use periodic driving to make a different kind of specially controlled periodic quantum system. So I want to start by thinking just very generally about why we work in the field that we do. And I would say that in general, in AMO and condensed matter, we tend to concentrate on the kinds of systems that we hope will eventually lead to useful properties. Not necessarily in this generation, but further down the line. And so we like to think about metals, for example, that have useful structural and electrical properties, or insulators, or phases of matter like superconductors that have electrical properties that you can't get any other way. And all of these things are studied actively in many physics departments and in many engineering departments. But what if you want something different from what you already have, right? You want more magnetism, a higher TC, longer quantum coherence time, something. How do you go about changing that? So if you're working in a naturally occurring system, these systems have the upside that they're stable and reproducible. You wouldn't observe it in nature if it wasn't immune to a certain amount of noise and disorder and temperature effects, and so they tend to be very nice from that point of view. But also stability is another word for rigidity. The same thing that makes these systems stable also generally makes it very hard to change any one of the properties. Like, you can't just continuously tune the properties of an atom, and it's highly non-trivial to substitute one element in a material for a different one. Chemistry will come and make you pay a price for that. And so you tend to be stuck with a very limited set of examples that are stable. And if you have, for example, behavior that you like in the terahertz, it's very hard to turn that into the same behavior at microwave or optical. On the other hand, if you think about a synthetic quantum system where you take some building blocks that you already know and you know how to work with, you can try to build them up into the unit that you want. It has the downside that you have to make it yourself, which tends to mean that large systems and reproducibility are hard, but you have a whole different set of constituents that you can use to try to build these things. And so you can try to make the same Hamiltonian appear in the microwave and in the terahertz and in the optical. And you just end up with a whole different set of constraints depending on the building block that you choose. And so you have a lot of different ways around. And so that's why some of these sort of man-made quantum technologies have been so fruitful. And so I work in the field of superconducting circuits. And so this is a quantum technology platform that combines the solid-state physics of Josephson junctions with microwave engineering to get really nice qubit and coherence properties with sort of, you decide what you want to have and then you try to make it, as opposed to you look at what nature gives you and you try to use that in the most effective way. And so in our toolkit, there are basically two tools. The first is the harmonic oscillator. And so for us, the most common one, and the one that I'm exclusively going to talk about today, is the coplanar waveguide resonator. And so this is a schematic here of coplanar waveguide. And so you should think of it as a two-dimensional version of a coaxial cable. There's a center conductor and two ground planes on either side, and you have a very tightly confined microwave mode. And then if you cut that mode, or you cut the center pin in two places, you produce a very strong reflection, which gives you a very tightly confined, one-dimensional standing wave for microwave photons. In practice, they actually look like this, so they're much longer and much narrower than what I drew, and we fabricate them with meanders like this to make them fit on the chip better. And the fact that we can do that is actually going to be key to realizing some of the physics that I'm going to talk about today. And if you're not an experimentalist and you don't want to look at CAD, this is a harmonic oscillator. The conjugate variables are charge and flux, and it's quadratic, and that's the end of that. So the other half of our toolkit is the superconducting qubits. So the most common one in use today is the transmon. And so this is the circuit diagram for a transmon. It's a capacitor in parallel with a Josephson junction. And this is what it looks like in practice. This is actually a device from our lab. So the blue and yellow here are in fact the blue and yellow sides of this capacitor. And at the Hamiltonian level, what this thing is an anharmonic oscillator. So instead of charge squared flux squared, it's charge squared cosine phi. And in particular, the transmon is in the limit where the EJ coefficient is much larger than EC, meaning that you can think about this thing really as a particle in a cosinusoidal well. And so the fact that cosine is not a parabola means that the level spacing in this well is unequal. And so that the lowest two levels down here have a different energy splitting from any of the other two, and it's these two levels that constitute the transmon qubit. As long as you don't drive too hard and too fast, you can treat this as an effective two-level system. Another thing that's very important is what I've drawn here. So this is actually two Josephson junctions in parallel. This is called the DC squid. And what that actually ends up doing is it gives you an effective EJ coefficient, which is magnetic field tunable. So you can dynamically change the depth of this potential and engineer the splitting of your qubit. And so you can tune this over octaves, 100 megahertz to 15 gigahertz if you want to. And so it makes these very flexible and very tunable, and with all of the problems associated with the words very tunable. And so what you can do, and what we always do, is we fabricate these qubits inside a cavity. Please don't lean against the back wall. The light switch is over there. Okay, so this is, this is our qubit, and actually this strip right next to it, if I could quite get that going, is the center pin of a coplanar waveguide resonator. And so the native Hamiltonian for the universe, as far as we're concerned, is this Jaynes-Cummings Hamiltonian over here. So we describe the cavity as a harmonic oscillator, the qubit as a spin 1/2, and the natural interaction between them is this energy exchange coupling over here, where you can convert a qubit into a photon and vice versa. And so what sort of level structure does this give us? Well, this is a picture of these levels in the special case where the qubit energy and the cavity energy are the same. And so over here on the left, if there's no coupling, you just get this infinite ladder of equally spaced states from the harmonic oscillator. But if you turn on the light matter coupling, then these degenerate levels split into doublets, and the size of the splitting depends on the number of photons. And so this is the Hilbert space that we live in, and you can think about it in two qualitatively different ways. The first is the more quantum computing perspective, where you decide that the spins are the system of interest. And then in that case, what you're getting here is a photon-mediated or a photon-controlled spin model. You use the photons in the cavity to manipulate, read out, and do gates on the spins. Or you can think about it the other way, that, you know what, I like photons. Photons are nice. And in that case, what the spin is doing is it's taking your linear photon spectrum and turning it nonlinear. And so the qubit is actually making the photons have an interaction. There's a different energy to 1, 2, and 3 photons, not just 3 times the single photon energy. And so we do sort of both of these perspectives in my lab. Okay, so that's the whirlwind tour of the building blocks of superconducting circuits. You now know all there is to know. And so what I want to talk about next is how we actually, in my lab, use these systems to make periodic lattice systems that both mimic and go beyond things that you can find occurring naturally in solid state systems. And so what is a lattice? For me, this is what a lattice looks like. So this is a photograph of a device from the Hauck lab at Princeton in about 2012. And so each one of these squiggly lines here is a coplanar waveguide resonator. We've now zoomed out far enough that you can no longer see the gaps in the center pins. And they meet at these little black dots. And so what is at those little black dots? So this is a zoom in. And so what's happening here is that the center pin of 3 different resonators is converging on the same spot. And so if there's a microwave photon that's rattling around in one of these resonators, then the capacitance in this junction region will allow it sometimes to hop onto the other one. And so we can think of this thing as a tight binding solid for microwave photons. There are lattice sites with energy omega naught, which is the resonance frequency of the individual CPW resonator, and then they can move around and jump from site I to site J with some strength T. And so for those of you that are familiar with tight binding models, I want to point out that the sign of this hopping coefficient is unusual. So in an undergrad quantum mechanics course, we teach our undergrads that the ground state of 2 coupled wells is the thing with the same phase on either site, and it's a universal rule that long wavelength excitations are at low energy and high wavelength excitations are at high energy. This system is the opposite. The long wavelength state is actually the highest energy in the system, and the rapidly oscillating things are at low energy. So if you're familiar with tight binding models, turn your head upside down. But it's just a global minus sign. Okay, and so now that's the lattice. And what we want to think about is combining that periodic array with qubits and thinking about what that does. And so this is an example of what the qubit is doing sort of to the photons. So this is old data from the Sholkov lab, just a single qubit in a cavity, spectroscopy. And so the qubit is degenerate with the cavity, and at low power we see 2 modes. And so these are the hybridized degrees of freedom, 1 qubit excitation and 1 cavity excitation. But you see as you go up in drive power, a series of additional resonances emerge. And these are the resonances where you drive to a 2-photon state, or a 3-photon state, or a 4-photon state. And you can see that they're very clearly energy resolved. So the nonlinearity of the qubit is so large that you can spectrally distinguish the individual photon numbers. And this is very typical in these superconducting circuit systems. The nonlinearities and the couplings are huge. This is single cavity data, but you can get the same kind of effect in a large system and hope to see sort of interacting photon effects induced by the qubit in the lattice. The other thing that we might want to think about is what's the interaction that the qubits get from being coupled to the photons. And so if you have two qubits in the same cavity, the most natural interaction for them is a photon-mediated flip-flop. One qubit de-excites, spits out the photon, the other qubit absorbs that photon. So that's this sigma plus, sigma minus term here. And if you do that in a single mode cavity, this has a very boring, trivial structure. Everything just talks to everything. But if you do it in a multi-mode system like a lattice, then you actually have an interaction that is mediated by all of the eigenmodes of the lattice in parallel. And this sum creates interference. And so if you do this in a 1D chain or a 1D photonic crystal, it's known that you will get an exponentially localized interaction. And this has been observed by now in several systems. And so a large theme of what my group does is we want to take these ideas of highly nonlinear interacting photons and a photon-mediated interaction that's controlled by the band structure and the spectrum of the photons and go to new lattices. Because doing this in CPWs is going to let us go to places that are really hard to find in any other system. And so there are two key features about coplanar waveguide resonators that really make it so that you can go to very interesting and unusual lattices. And so the first is that our resonator is in a certain sense flexible. And so these are CAD drawings for two different resonators. And we look at them in the optical and they look totally different. But if you're a microwave photon confined to this waveguide, then the entire world is just following this waveguide until you get to the end, and then you bonk into that capacitor and you turn around and come back. And so the frequency of this resonator depends only on how long it is, not on whether it has one wiggle or three. And the hopping coefficient is not set by a potential that creates an orbital and that has an overlap with the next site. The hopping coefficient is entirely determined by how big of a capacitor we put there. And so what that means is that these two lattice sites can be completely equivalent from the point of view of a microwave photon. So I can pack an equivalent lattice site into a very different footprint, depending on what I want to do. And so we can make a big array that's perfectly periodic, but you can also make an array where you use different shaped resonators and get a packing that would not normally be allowed by crystallography. And I'll show you an example of that on the next slide. The other thing that's actually really, really important for understanding these systems is that the lattice site is not a point-like object. It's a one-dimensional object with two ends. And so if I look at this device, most people would pick out a hexagonal lattice, but what's really going on is that the sites correspond to these resonators. And then there's a hopping shown in red if the ends of the two resonators touch. And so this particular device realizes a Kagome lattice. And it turns out that this is a very general mathematical object called a line graph, and that every lattice that we make is going to be a line graph. And these are very special lattices with unique properties. Every single lattice that we make is going to have a flat band, which is already a miracle. Okay, so that's the toolkit. And what does that give you if you combine qubits in the lattice? So one of the tricks I said that we had is that we are not limited by the conventional rules of crystallography. And so this is a device that we made when I was a postdoc with a resonator array that looks like a periodic array in a negatively curved hyperbolic space. Photons moving in that thing think they live in negative curvature, even though it's fabricated on a flat 2D substrate. And working together with Alexei Gorshkov's group, we were able to show that if you put two spins into this lattice, then the photon-mediated qubit-qubit interaction that's generated inherits the hyperbolic structure of the photons. And so you can make flat things, you can make curved things, you can make ripples to your heart's content. And then the other thing that we have really going for us is that we have an overwhelming tendency to generate flat bands, which are very rare features in solid-state physics. The Kagome lattice is the canonical example, but we've been able to use graph theory tricks to generate many, many, many more, including ones where the flat band is entirely by itself. And so this is an example that has a flat band that is far from any other bands. And if you look at that thing and you ask what sort of photon-mediated interaction does it give, it actually gives a short-range frustrated magnet. And so this is the kind of physics that we wanted to access in my lab and that I came here to start building. Okay, and so what I want to tell you about next is what we've actually done. And so before I started here, all of the CPW lattice devices that had ever been made did not contain qubits. They were either highly disordered with lots of qubits in a trivial lattice, or they didn't contain qubits at all. And so the task that was for us was to take this flexible resonator connectivity and add the qubits in without ruining the nice microwave pattern and learn how to measure these kinds of systems. And that's what we did. And so we decided to target this particular 1D lattice. We chose this 1D lattice because it has a nice, being 1D, it has a nice bulk to boundary ratio, and we can get access to it from the side with flux bias lines, and because it has just about every kind of dispersion relation you could imagine in a 1D system. It has quadratic band edges, it has linear band crossings, it has flat bands with a gap, flat bands without a gap. This just had absolutely everything. And so we thought this was the perfect prototype to set out and actually do. And so this is the device that we designed. And so it's 9 unit cells of this lattice, starting here, going in an S-curve, and going around. And highlighted in red here is 1 unit cell. And then in orange, we have on-chip flux bias lines to individually control 3 qubits, which we write here, here, and here. And those of you with fresh glasses prescriptions or eagle eyes will notice lots of purple caterpillars in this particular device. And so those are actually the qubits. And so we have to actually punch a hole in the resonator to put the qubit in. And so what we actually do is we write the capacitor paddles of the qubit everywhere to reduce the disorder, and we only write the Josephson junction, this very small little red loop here, in the sites where we want to have a qubit. And so this gives us a low disorder array with individually controllable qubits at sites that we chose. And so this is the device that was made. So this is the device right after photolithography. And so now when you look at it, black is superconducting tantalum and white is looking through the gaps in the lithography pattern to the paper, the white paper behind. Once it's fully packaged, it's much harder to see. What you're looking at here is an infinitude of wire bonds. So Maya communed with the wire bonder gods for many hours and was able to fully package this. As I said, it has 9 unit cells, 3 working qubits, and 2 transmission ports. And we cooled it down for the first time during March meeting 2023. And in a reversal of the usual method, my students went to March meeting and I was in the lab taking data. Kellen, a brand new grad student, was sitting there with me. This is a nicer data set than this, but this is kind of the basic measurement that we can start to do. So let me explain what we're looking at. So this is microwave transmission as a function of flux. And so if you look at one horizontal cut here, you'll see a series of peaks. And they're showing you the locations of the cavity resonances, but the qubit is voltage tunable. And so as we change the qubit applied to the voltage applied to the qubit degree of freedom comes racing through the lattice modes, leaving behind this trail of avoided crossings that you can see. And so this is the first indication that we have both a band of narrow resonances coming from the lattice and a live qubit, which is strongly interacting with these modes. If we zoom in down here at the bottom, you can see these avoided crossings more clearly. Transmon qubits tune periodically with applied magnetic field, and so this is actually going down to a minimum and back up. Okay, so yay, it's alive. We were incredibly happy. But then comes the hard work of proving that we made what we wanted to make and that we can control it and realize the interactions that we wanted to have. And so skipping rather a lot of work in details, what we were most interested in is actually the second harmonic modes of this lattice. These are full wave modes that have a symmetric on-site wave function, and they are actually the ones that realize this band structure here. And so now we can look in transmission, and unfortunately the second harmonic is higher in frequency where things are messier. There's a lot more leakage through the package, and so you see narrow features and you see some avoided crossings from the qubit going by, but there's a lot of mess. Those of you with eagle eyes will also notice that there's 3 sets of bands here, and there appears to be only sort of like one clump of stuff here in the middle. And so what's going on? And so what's going on is that this transmission measurement is actually not a really good way to look at this device, because you have to get the photons in and you have to get them back out. And so what we discovered is that if we do a nonlinear measurement, we can do a much better job. And so we were able to generalize a technique called two-tone spectroscopy, which is standard in the field. And so the basic idea is if you have a qubit in a cavity, then you put a weak monitor tone at the cavity, and then you try to flip the state of the qubit. And if you flip the state of the qubit, it's nonlinear, and what it will do is it will move the cavity out from under your probe if the state of the qubit changed. And so that's the standard way, actually, that superconducting qubits are read out. But it's just a general phenomenon of nonlinear degrees of freedom. If I change the occupation in my nonlinear oscillator, it will move the linear oscillator that it's attached to. And so this is data taken that way. So we're monitoring one cavity mode, and now we're scanning a very strong probe. And whenever we hit something, there's a dip in transmission. And so now we see 3 sets of dips. We also no longer see lots of background, because the background is coming from signals leaking around our device that don't couple to the qubit, and only the lattice modes strongly couple to the qubit and are able to give us signal. And so we get a very nice background-free measurement. And if you compare the locations of these peaks to the expected density of states, we get a pretty good agreement. And so what this is telling us is that we were able to make that big, complicated device going around in an S-curve, fitting in multiple different shapes of resonators, cramming in live qubits, dead qubits, and flux bias lines, and our nice resonator array survived. So we know now how to build these devices. Sure, I guess.
So these 2 bands correspond to the orange and the purple, and then naively, I think the flat band, the photons cannot propagate, right? So they won't make it to the other side.
Yes, and that's a lot of the reason why there's essentially no transmission signal here, but there is nonlinear signal, because I can get the photons in, they talk to the qubit, and then they shove my monitor mode away. And so that was one of the things that we discovered, is that these localized modes that you have a lot of trouble seeing in linear spectroscopy, because they're localized, in fact, couple well to the qubit and give nice signal in this nonlinear method. These are just very narrow, and so actually, you might notice some very thin lines here. Those turn out not to be glitches. Those turn out to actually be the cavity modes, which we would have missed on the first pass without the nonlinear spectroscopy. Okay, but so far, we've not really seen the qubit itself except by sort of proxy. We've seen the nonlinearity that it creates, and we've seen the avoided crossings, but this mode-mode spectroscopy data is using the same technique that we would use to find a qubit. We're just pounding on it really, really hard. And so the next thing that we do is we start to look in the band gaps where the qubits are not photon-like, and so that we wouldn't see them in our normal measurements. And so now we're doing this same nonlinear spectroscopy, we're just not pounding on it quite so hard. And you'll see that I've now added 2 more patches of data. And so these are nonlinear spectroscopy showing a qubit-like mode in the 2 band gaps. And so what's happening is that the bare qubit is tuning through like this, coming up to a maximum and going back down, and this is an avoided crossing primarily with our flat bands, and this is another localized state emerging up at the top. And so we can see the qubit itself, even though we're working in a very multi-mode environment, which is not normal for superconducting circuits. But this is still not entirely what we wanted, because we made this device really to go after the photon-mediated qubit-qubit interactions, and we could get that, but in this range, the qubit is very hybridized with the photons. So 2 qubits in this frequency range will exchange real photons and lose energy by those photons. And so what we actually want to do is go down here into the band gap, farther away from these bands, where now the 2 qubits will exchange virtual photons, and so now they'll get interaction without picking up so much of the photon loss. And so that's what this data is, and so for each of these scans, we fix the frequency of 1 qubit and scan the other one across, and we get an avoided crossing, which gets larger and larger and larger as we approach the bands. And in the middle, we actually see signatures of the 2-photon transition to the doubly excited 1-1 state. And so with that, basically, we've shown that we can make low disorder arrays with qubits that don't respect sort of the natural crystallography of the natural periodicity of the Hamiltonian, but the Hamiltonian is still good, and that we can both verify the photon modes and measure the qubits. So this work is on the archive and under review at the moment. Okay, and so with that, I would like to wrap up the spatial lattice part of my talk and switch gears to start talking about periodically driven systems instead. And so now we have something that's periodic in time rather than periodic in space. If you're a mathematician, you don't even bother to change variables. If we're physicists, then we will. And the reason to sort of think about these periodically driven systems is that the constraints on your periodicity depend on how you made it. And so we talked about the spatial lattices with coplanar waveguide, that there's a lot of flexibility that we can make, but we're still constrained by what we can fabricate. On the other hand, if we make our periodicity by periodic drive, then now it's a question, how snazzy can we make the controls in terms of what we can arrange? And so that's what I want to tell you about in the next part of my talk. And I want to start actually with a little bit of a history of this project. And so most projects in synthetic quantum systems, they start, I have identified the following Hamiltonian that I would like to make. Then you figure out how to make it, and then you try it, and when it doesn't work, you do a feedback loop over there until you end up with Hamiltonian I wanted, Hamiltonian I got, and you want them to be the same. This project that I'm going to tell you about now actually really started with a discovery in the lab of an effect that we had no idea about. And so we were working on implementing something called a topological flow K pump. We will not get into that entire black hole. But around April or May of 2024, these 2 scans appeared in the lab Slack channel. And so this is the qubit state as a function of time. And so what's going on here? We were trying to drive an oscillation, and indeed the qubit is oscillating. Good, step 1. It looks a little funky at early times, but then it cleans up. That's not normal, but maybe we accept some gift horses, right? Things get better at long times, we're grateful. It looks like a coherent oscillation, but there's something very, very, very strange about this data, which is that the lifetime of this qubit is 10 microseconds. And this time axis is 100 microseconds. So we have a quantum degree of freedom with a lifetime of 10 microseconds doing what looks like a nearly perfect coherent oscillation for 100 microseconds and having no intention of stopping. So how on earth does this short-lived qubit show this kind of long-time dynamics? It took us about 6 months to figure out exactly why and really verify all of it, but that's the story that I want to tell you now. How did we make a perpetual motion machine, which is not a perpetual motion machine? Okay, and so the general context of this is that we are looking at a periodically driven system, so these are called Floquet systems, and the idea is that the idea of Floquet engineering is that by applying periodic drives, you can make a new Hamiltonian that's different from your natural laboratory frame Hamiltonian. And people have used this all the time to make new kinds of qubits, topological bands, sort of the world's your oyster, except that whenever you do Floquet engineering, the periodic drive induces heating. This is known to just be a general rule. And this heating comes from a combination of two effects. So one is that you are mixing the laboratory frame excited states with the laboratory frame ground state. And so your periodically driven states are inheriting decay and dephasing from the excited states. You're also driving very strongly, and so you can have high order couplings in the Hamiltonian sort of rocket you off into weird parts of the Hilbert space from which you never come back. And so the data that I showed on the previous slide was actually an example where you could take your complicated, strongly driven, messy Floquet system, which should be heating, and actually take all of that heating back out again just by coupling it to a very simple cavity. And so that's the story. So we're going to consider the simplest possible Floquet model known to man, I think, which is a spin 1/2 in a rotating magnetic field of strength B0, rotating at a frequency omega mod, and we're going to couple that to the cavity. And so the intuition that you should have is there's an atom in a cavity, and this atom has a decay rate gamma and a coherent drive B, which is trying to move the state of this atom around. And then that atom talks to the cavity, and the cavity has some decay rate. And now, because the state of the qubit is being changed so dramatically by the drive, qubit decoherence leads to heating. These states are very strongly time dependent. Any state that you're in has the ability to spontaneously emit, and you can go pretty much anywhere else. But the cavity is not being driven, and it turns out that this cavity decay can give you cooling, even though this part of the Hamiltonian is super messy and time dependent. And so the way that we actually realize this is with this chip here. And so we have a few ingredients. So there's a qubit shown in yellow, and it's coupled to two cavities. The one shown in red is what we call the readout cavity. So we're going to use this to measure the state of the qubit and apply some of our drives. And then it's coupled to a high Q cavity in green, which is our boost cavity, which is the one that we're going to interact with. It's called the boost cavity because it was designed for a project called boosting. It was not doing that at the time. And then also the qubit has, shown in orange, a flux bias line. And so this is going to let us achieve the Hamiltonian that I wrote on the previous page, not with a real spin 1/2 in a magnetic field, but with our qubit under control drives. And so our X magnetic field is actually going to come from the strength of a microwave drive, and our Z magnetic field is going to come from this flux bias line, detuning the qubit with respect to that drive. And then the cavity, there used to be a word there, the cavity detuning is now the drive to cavity detuning, and that lowers that energy significantly. And so the kinds of experiments that we're going to do are now all going to look like this. So we start with the qubit in the ground state, and we will have an optional pi pulse that lets us flip it to the excited state if we want to. And then we adiabatically map the bare qubit states to being aligned with the applied magnetic field and rotate up to the to the equator of the Bloch sphere. And then we rotate the magnetic field for some amount of time, tau, and then we stop and check what the qubit is doing. Okay. And so to understand what's going to happen in this system, I find it very helpful to look in the plane of the X and Z magnetic field. And so this is a cartoon of what happens if the qubit is far detuned from the cavity. So this circle here is the line that the magnetic field traces out. And the qubit state is going to follow that field around in a circle on the Bloch sphere. And then this dashed line in red here is the magnetic field that it would take to bring the qubit into resonance with the cavity. It's the line where the Zeeman energy is equal to the cavity detuning. And we put here a width, which is the strength of the cavity coupling. And in this regime, the qubit will follow the magnetic field and not really care about the cavity because the energy mismatch is too big. If you go to where the qubit is resonant with the cavity, you have an energy mismatch in the opposite direction. The Zeeman energy is too big for the cavity. They don't talk to each other. And so the place where interesting physics happens is when the Zeeman energy of the qubit matches the detuning to the cavity. And in that regime, this is what the level spectrum looks like. And so this magnetic Hamiltonian has two eigenstates. We're going to call them phi plus and phi minus. They correspond to the qubit being aligned with the magnetic field at all times or anti-aligned with the magnetic field at all times. And there's one copy of each of those for every photon number in the cavity. And so phi plus and phi minus are rotating in time. And at parts of the cycle, they each contain the qubit excited state. And so that means that the laboratory frame spontaneous emission of the qubit has the ability to go up as well as down. When the qubit de-excites in the lab frame, it can excite in the effective magnetic picture, or it can de-excite. And so the qubit decay rate gamma is just causing a mess. On the other hand, the photon decay, the photon does not have the same inversion. And so the photon decay goes uniformly downward to lower photon numbers, trying to head to this zero photon sector. And now, if you are at Zeeman resonance, then the excited magnetic state with no photons has about the same energy as the ground magnetic state with one photon. And so this phi plus can interconvert to phi minus and then decay to phi minus and zero photons with the cavity decay. And so the cavity decay is trying to drive everything towards this particular state here, phi minus with no photons. So as long as the cavity decay is faster than the atomic decay, this becomes the attractor of the dynamics. So what does that look like in practice? Okay, so now we're going to do the careful version of the data that I threw up at the beginning of this section. And so if we start by looking at far detuning, and so what we do is we prepare either initially aligned to the magnetic field or initially anti-aligned to the magnetic field, and then look at the dynamics as a function of our rotation time. And so you start out with two opposite phase oscillations. And then without the cavity, these decay over time to a general mess. You've got a mixed state of both. But if we now come closer to the cavity, we start to see qualitative changes. So we start with two opposite oscillations, one of them aligned, one of them anti-aligned. But then the orange data that starts in the phi plus state loses contrast more quickly, and then it reemerges in the same phase as the experiments that were started in the opposite phi minus state. And so what we're starting to see here is the emergence of a unique non-mixed steady state. Contrast isn't high, but it's there. And then if you go closer to resonance, you see much larger oscillations. And here now we have included the T1 time of the qubit just to compare the natural lifetime of the qubit to the length of these oscillations. And you can see that the oscillations appear to be going on forever. We went out to about 200 microseconds and then we got bored because nothing was changing. And so as far as we're concerned, 200 microseconds is infinity, and this will go on forever. Let's see, I'm running a little short on time, so let me try to be quick. So the other thing that we did here is the measurements that I've showed you so far are with basically a diabatic turnoff as much as we can. So we try to measure the bare qubit eigenstates as a function of time. So that's why we get these oscillations. But we can also do an adiabatic turnoff where we try to map the eigenstates of our magnetic Hamiltonian back to the bare qubit eigenstates, and that gives us a much more direct measure of the actual phi minus population. And so what's shown on this slide is a series of detunings. So here the magnetic field is a little smaller than get to resonance, and it gets closer and closer and closer. And this color code matches these curves on the left. And so what we do is we start either mostly in phi plus or mostly in phi minus and watch the average phi minus population as a function of detuning. And as we get closer and closer to resonance, the steady state population goes towards 1, and you actually approach the steady state faster and faster. And so this peaks out at about 90% steady state occupation of phi minus, which is actually shocking because this device was not designed for this experiment. And actually the cavity lifetime is only 4 times, the cavity decay rate is only 4 times longer than the qubit decay rate. And so I keep telling you that to get this to work, you need the cavity decay to be fast enough. This is the longest lived cavity in my lab that's doing this, which is the exact opposite of what you would actually want. So it's doing remarkably well. Okay, and so then let me try to finish up by giving you an idea of the scope of this method. And so this particular example is realized for a 2-level system with a slowly varying drive, because that's what we can do in the lab. But it turns out that this phenomenon is much, much more general. And so this is a calculation that was done by our theory collaborator, Alicia Chandran at BU. And so she was looking at the fidelity to the phi minus state now versus the modulation frequency. So the data that I showed you before is all down here at essentially 0. And so what you can see is that there are some very nice dark lines where you get very high fidelity to the phi minus state. You just have to use the actual eigenenergies of this much higher frequency drive problem as opposed to the bare static Zeeman energy. So this idea works for arbitrary drive frequencies, and we were also able to show that you can do it in a much larger Hilbert space. Like we took a spin 1/2, it's got 2 states, we drove it to 1 state. You could worry that if you take a more complicated system, this breaks down. And so this idea is going back to a topological flow K pump. Very, very broadly speaking, this is a qubit in a cavity with a periodic drive, and if you set it up right, it channels photons 1 by 1 from the drive into the cavity. But in practice, if you actually do this with a real qubit, you'll get errors in the qubit. So if you look at the photon number versus time, you see that most of it follows this red line, which is the ideal behavior. It goes up and up and up, but a bunch of the population has sort of fallen away and lost the pumping. And so what Anusha's student David was able to show is that if you take this model and you add a low Q cavity, you can use that low Q cavity to clean up the errors in the qubit and keep the high Q cavity pumping very nicely. And so to do that, we would do this semicircular magnetic field, where in the vertical stroke, you are doing the pumping in the cavity that you intend. And then in this outer portion, you are on Zeeman resonance with your low Q cleaning cavity. You fix errors in the qubit, and then you go back around for more pumping. Okay, so hopefully I have given you a flavor of the kinds of things that we do in my lab with synthetic lattice systems, and that I've convinced you that circuit QED can make very interesting systems that are not naturally available in solid state crystals, so that we can go to curved spaces. and that we've been able to actually do some really potentially useful things, showing cooling and stabilization of Floquet states, which normally die via heating. And so we're hoping to actually do stabilization in larger systems, go up to the hyperbolic state with qubits, et cetera. Hyperbolic lattice with qubits and things like that. And so now I want to wrap up by thanking the people that made this work possible. So we're supported by a large number of funding agencies, and without them, we would not have been able to do this work. Also, I really must thank the graduate students who actually did this. You know, they've been in the lab working hard, and they've produced an amazing amount of excellent work, most of which I didn't have time to talk about. And so I just want to take a brief moment to acknowledge all of the other hard work that's been going on that I haven't talked about, where we've been looking at new ways of making non-reciprocal on-chip devices for superconducting quantum computing. We've been looking at nonlinear wave mixing and Kerr processes in the coplanar waveguide lattices. Another contingent has been looking at ultra-stable qubit readout using the Pound-over-Hall method. And we have a brand new project trying to push the operating frequencies of superconducting qubits from where they are now, which is below 50 millikelvin, up to something compatible with a less expensive piece of equipment than a dilution refrigerator. Okay, and so then with that, let me get back to the faces. And so the students that have worked on the spatial coplanar waveguide lattice project, and those collaborators are shown in red, and the folks responsible for the Floquet stabilization project are shown in purple. Thank you very much.
So in the last part of the talk, you had this Hamiltonian on the drive magnetic field. You had sigma X and sigma Z matrices.
Yes.
The question is, can you also get sigma Y, the third one?
We could, yes.
Which of course I think is required for this topological pump.
Yeah, for the topological pump, the sigma Y will come from the cavity. But in this kind of a system, basically the cosine component of the microwave drive is sigma X, and the sine component is sigma Y. And so we could do sigma Y, but for this, we had no need to.
I think they would have to be different frequencies.
Yes. For the Floquet pump, the cavity will be in the XY plane at one frequency, and this classical drive will be in the XZ plane at a different frequency.
So I'm moving in this direction.
Work in progress. Let's see. Billy is at the end of the next row. He can tell you where that is right now.
So this T1 plot that you showed seems extraordinary to me, and I was wondering if this can be extended to other platforms, let's say trapped ions, extending the coherent lifetime.
So what I probably should say is that this is not exactly making the coherence infinite. What this is doing is resetting errors. So it's oscillating at a specific frequency and phase. There's a spontaneous emission event, it gets all screwed up, and then the cavity locks it back in place. And so the coherence, the fact that the coherence time is 10 microseconds, what that translates to is the contrast or the purity of the steady state. And so there are examples that people have worked out where you might be able to use a version of this to stabilize a Floquet engineered qubit. But there you have to work much harder because you have to make sure that regardless of what error happens, you go back sort of to the same state. You don't want the exit and return process to modify the wave function or collapse superpositions. So I think there is prospects for that to work, but it's much harder. Alicia is looking at trying to use this cooling scheme on spin chains, and at least numerically, it appears to be working pretty well. So it has some legs, I believe.
Alicia, yeah, I was gonna, so you've developed lots of methods, and you've already done some lattices before, but I'm wondering what the next, or what your dream lattice problem would be, or some.
I really want to go hyperbolic. I think that's, for me, I feel like that's really where the frontier is.
Say again?
I want to go to hyperbolic lattices.
What do those look like?
So that was the very first slide. Yes, if I go all the way back.
Make the Louis Chateau's
There we go. Yes. So that's the hyperbolic one. And the reason is because that it's well known from classical computation and graph theory that there's things you can do on a hyperbolic graph that you just can't do on something that has Euclidean structure. And it's well known that there's things you can do on a quantum computer that you can't do on a classical computer. The land of hyperbolic quantum things is hard squared. So we don't really know what lives there, but I think some really interesting things might be there.
I have two very short questions. Thanks for the talk. Do you have any data or can you comment on the number of unit cells and how it affects how you can resolve the bands? How did you know 9 is enough? And then
Well, yeah, and so this lattice is maybe particularly small. It packs particularly poorly. So we should be able to do much larger on other things. And so what it ends up doing is you sample the bands a little bit. And so as far as I know, this should still dominantly show the structure, but for larger things, we eventually do want to go to bigger systems. There's ways that we can try to make this more compact.
and on the second part of your talk, am I correct in like the kind of the long T1 that you see is not particularly a topological effect, is that right?
This is not a topological effect at all. This is something much more akin to optical pumping. And so if I have a few static levels and I can tune the dissipation, none of my AMO colleagues are surprised that I can systematically depopulate one of them into the other one, and that if an error happens, I can put it back. What's much more miraculous is that there's these complicated time-dependent drives going on, and that I don't need to use a complicated time-dependent dissipation to fix the errors in my complicated time-dependent states. But once you accept that it works, it is just optical pumping. It's just any of us that sat down would have been like, yeah, something's going to go wrong. And apparently it goes right instead.
So I guess going back to your answer to Kevin's story, I mean, the hyperbolic geometry being packed into Euclidean space means that you get weird packing with qubits. So how scalable is this story?
So we can, I have dreams of going about one shell larger than this. But we can only really make hyperbolic flakes of a given size. This is true.
So how many?
This is 140 resonators, what's shown here.
Yeah. Shell higher would be something.
Probably about 3 times as many. I think this goes as like 3 to the something or other.
The quick follow-up is: is this structure really tied to planar structures, or are there hopes of like things jumping over?
So the fabrication gets much more challenging if you go to a large number of interconnects. So with a wire bond and a bond pad, we can hop over like once. And probably eventually for flux bias lines, we will need to do that, but you're talking about like a few connections, not trying to make a 3D structure. More advanced fabs can do flip chips, so you can make sort of like a bilayer type structure. And we may eventually go that route, but that's a level of fab that we would have to send out to MIT Lincoln Lab for, not do ourselves, I think.
The last question, someone.
Thank you for the great talk.
just building up on the question that Victor Yakovenko asked previously, if you were to able to generate this like sigma y term as well and have all three at the same time, how would you measure this topological signature of energy pumping between the drives?
We measure the photon number as a function of time.
I see.
Like, that's the goal, is to really measure the output photons themselves, which we are working on in the lab right now.
Thank you.
Hasn't happened yet.
Okay, well, Alicia is going to be here, so you can continue asking questions.